Okay, I've got a table full of data. I've got a suggested relationship. What I need to do is see if this relationship does seem to model the data. So I've got to reduce it to a linear form using logs, as it turns out. And the variables are t and f. Okay, so f is a variable, t is a variable, but k and r of constants to be found. So in order to find a working relationship, I need to know what the numbers k and r are. Okay, t, one of the variables, is tucked away as a hidden power. So that's what gives away to me that I need to use logs. So we do the standard thing with logs. We start with f equals k times r to the power t. We do log of each side. So log of f is going to equal log of k r to the t. This is log of something times something. So using laws of logs, laws of log of f equals log of, it's a product, so log of the first thing k plus log of the second thing r to the t. Okay, and then the r to the power t, there's another law of logs I can use. So log of f equals log of k as before, plus, and this becomes t times log of r. And of course we're using log to the base 10, which is what we use unless there's a good reason not to. So this is now a straight line form if I compare it with one of our standard equations of a straight line. So the one we often like to use is to compare it with y equals mx plus c. Okay, I need to find my variables, don't I? So where's f? F is in this term. It's living inside log f. Where's my other variable? My other variable was t. Okay, which is here. So this is going to be something times, well, t is in my first column, so that's acting like an x, and f is kind of in the y column. It's the dependent variable, but it's log of f that has to match with my y. This is going to be mx plus c, so the x bit must be here. This must be at my mx bit. So this must be my c plus, and this must be mx, but I can see the variables coming first. So actually I'm going to write xm here. Okay, from the calculator, if we use calculator regression, the calculator likes to call it straight line y equals a plus bx. But once again, because of the position of that t, I'm going to call it xb. Okay, so we'll come back to this later when we're actually going to interpret our gradient and intercept. But for now, we need to know that we need to tabulate, well, t I've already got, but I need log of f. So in my updated table, I've given myself a t column. Okay, that's just going to be a copy of what we had before. And then for log of, this should say log of f, not log of p, sorry about that. Okay, so for log of f, I've got to take each value. So 12.6 is the first one. Log of 12.6 gives me, my first value, which is 1.10. So I'm going to have 1.10 as my first entry there, and we're going to take it from there and fill in the rest of this table. And there it all is. That didn't take long. And then we need to set up some scales and plot these points on suitable scales. And if this relationship is a good model, they should form a straight line. And if we look at this graph, we can see that that is not too bad for a straight line at all. Okay, so I could comment, yes, the data does seem to support the relationship, and I need to draw in my line of fit. Now, depending on how I want to work things out, I can either use my diagram to work out the slope and the intercept of this straight line, or I can use the regression functions on my calculator. Now you need to read the exact wording of the question so that you are using the one that's required. Sometimes you'll be allowed to use your calculator, sometimes you may not be. I'm going to do both. So I'm going to get the gradient and the intercept using my graph, and then I'm going to use my calculator to check it. So we've got both ways. So I need to choose two suitable points on my line. They can be anywhere as long as I can read the coordinates clearly. So I think I can read here, there's a point with coordinates, what would that be? Below 10. That would be 8.5 for my x coordinate with a y coordinate of 1.0. Okay, and I can find towards this end of the line I can find, I think I'll have, looking for one where it goes through a fairly exact grid point. That's not too bad there. So that is 43.5 for x, with a y coordinate of 3.25. Okay, so armed with two data points, I don't know if you can read that, I've written those coordinates there. What does it say there? 43.5, 3.25 is what I made that point to be. Alright, so I need to draw in my triangle joining those 2 points I've selected. So I'll draw the horizontal, I'll draw the, that was a very bad horizontal, I'm going to have another go at that. I'm going to draw the horizontal. Okay, and from here, down from here actually, I'm going to draw carefully a vertical down from there. Okay, so that's the triangle I'm using, but in fact I'm going to find these distances just by subtracting coordinates. So for the x's, I've got to do the difference in x, so the x step is going to be 43.5 minus 8.5, which I can do in my head, that is 35. Okay, and my y step, this was 3.25, so I'm doing 3.25 minus, this was a 1.0. Okay, I can do that in my head as well. This is 2.25. So my gradient, okay, that's going to be the change in y over the change in x. So that's 2.25 divided by the change in x, which is 35. Okay, so I can do that on my calculator. So 2.25 divided by 35 equals 0.064263. I'll record it to 3 significant figures. There we go. All right. And now I've got a gradient, I can plug on and find the y-intercept. However, I've got to be careful here. Can I just extend the graph back and cross the y-axis? No, I can't, because I have a broken scale here. This value here is actually, on this scale, it would be 5, not 0. So I can't use the graph to read off the y-intercept. Sometimes you can. If you haven't got the y-intercept visible, then what I need to do is use my equation together with a data point. So I've got a point here where the coordinates, t was 8.5, and the y-coordinate, the y-value, log of f, was 1.0. So I need to find a way of using that data point, 8.5, 1.0, as well as this gradient, 0.643. Okay, so here's my gradient and that data point we talked about. So now I have to go back and do my matching up with the equations. So log f and t are boxed because they are the parts of the equation based on my original variables t and f. Okay, so my log f was the y value that I plotted, and the t value, the variable there, on the x-axis, I had x, so x and t are the same thing. Okay, so I can match up the other things. So I can now see that the gradient of my graph, okay, so the gradient, which is my m or my b, okay, has to equal the log of r, that part of the equation. And I'll be using that later to get the value of r. And my intercept, which is what I'm trying to find now, so the intercept equals A or C, all right, which will be matching this log k, which I'll be coming back to. But what I need to be able to do is substitute my gradient and this data point into one of these equations, okay? So I'm going to be using 0.0643 as the gradient, okay? And the data point, this was a value plotted on my x-axis, so that's an x, and x is the same thing as t. Okay, and this 1.0 value was a value of my y-coordinate, so that's a y, or a log f. Okay, so my data point, okay, I'm going to put the y value in, 1.0, okay, equals a or c, the intercept I'm trying to find, okay, I'll use c, plus the x value, so the x-coordinate of my data point was 8.5, times m or b, which was the gradient, which is this 0.0643. 3. So this equation is going to tell me what c is. Okay, 1.0 equals c, the intercept, plus, and then I need to do this other bit on my calculator. So my calculator is telling me that that calculation is 0.54655, and I want to find out what c is, so I need to take away this value from both sides. So c is going to equal 1.0 minus that answer. So 1 minus that answer is 0.453 to 3 significant figures. So I now have an intercept and I have a gradient. Okay, now as promised, I've got those from the graph, but I'm just going to double check those against the stat mode on my calculator. So I need to put my calculator into the correct mode. So we do mode 2 for stats, and then the one you always select is the one which is a plus bx, and this is a reminder of what it thinks y is. The formula it's using for y is y equals a plus bx. So I select 2 from there, and now I enter my data value onto the calculator. Data values, I should say, and that's what they look like. So that's my table full of data. In order to get the values of a and b, I press AC to get away from the table. I use the shift button. I use the 1 button because it's got stats in yellow above it, and I ask to do regression calculations. So 5, and the value of b, that's one we worked out first, the gradient. So 2 for b, it's telling me b equals 0.0641, which compares pretty well with the 0.0643 that I got by hand. And for my a value, shift 1, 5. For my a value, I'm getting 0.455, and the value I've got here is 0.453. So I'm getting pretty good agreement. So use either the drawing method or the calculator method, depending on what the question paper hints at, but I would always use the calculator method just to confirm that the values you've got by drawing aren't too wildly out. Okay, so now we've got a gradient and an intercept. I now have to convert those back into values of the missing constants. So the matching's already done here. Here's my rearranged equation using logs, and I want to match that with y equals mx plus c or y equals ax plus b. I've used m, I've written m or b here. I've already done this matching, so m, the gradient, okay, here it is. M, the gradient, matches with log r. So I know that the gradient, which is, I now know, 0.0643, is, yes, it was m, but it is, I know that matches log of r. And I want to know what this value r is, so I need to undo the log. So r is going to equal 10 to the power of 0.0643. So on my trusty calculator, 10 to the power of 0.0643 equals 1.1595. So that's 1.16 to 3 significant figures. Okay. And the intercept, okay, which we know is my value that I got for the intercept here, 0.453, okay, is my value of, well, it's a or c, it's my value of log k. So once again, I've got to undo the log, so k is going to equal 10 to the power of 0.453. So let's do that. 10 to the power of 0.453. And that's giving me a value of 2.837. So that's a value of 2.84 to 3 significant figures. So I have got values of r and k, which is where we came in. We said we wanted to know what those constants were. So if I put those into the equation, f equals kr to the t. So the given relationship was f equals k times r to the power t. And I now know that that can be written as, with my values, 2.84 is k times r, which is 1.16 to the power of t. Okay, so f equals, I should write f equals 2.84 times 1.16 to the power of t, and now I can use that to predict some values that weren't in the table. Okay, now just for fun, what we can do is actually use Excel with this formula and the original table of data to see how good the predictions are. So here I've pasted the original data we've had. Here I'm going to put my formula in. So I want to do equals. I think that this value, 12.6, is formed by doing 2.84, we had in our formula, 2.84 times the input value, the 10 value, to the power of, no, sorry, it's not, it's my R value, which is 1.16, 1.16 to the power of my input value here. And if I get it to work that out, it's giving me 12.52. And if I copy that all the way down, like this, okay, if I compare the values from the formula with the original data points, you can see the fit is extremely good. So I'm quite happy with that. So in summary, that's how we can start with a table full of data and a proposed relationship. This is an exponential law, and get the actual relationship that it stands for. So I hope that makes sense.